Alrighty, welcome to the notes video for lesson 3-4. This one is about percent change and percent error. We've been using the proportion or the equation to do percent problems. These are just two specific kinds of problems. You get to pick which way you do it. Most of the time I will use the equation, but you are more than welcome to use the proportion version. These are two pretty basic ideas. If we are wanting to find a percent change, the whole purpose of that is if something changes, how much it changes may not be the best measure of how significant the change was. For example, if I lost 5 pounds or a baby lost 5 pounds, those are two hugely different things. So if me being close to 200 pounds, I lose 5 pounds, that's not a big deal. A baby that's like 15 or 20 pounds, if they lose 5 pounds, that is like catastrophic. So we can use percent change to determine how big of an impact or how significant a change is. And sometimes it'll ask for the percent increase or the percent decrease. And all that is if the change is an upward change. If something goes up, then that's a percent increase. And if something goes down, it's a percent decrease. But they're both percent changes. So percent change is simply how much something changes compared to what it was before the change. We always need to compare it to the before picture because that's what actually changed. The before picture changed. So like if my weight is 200 pounds and I lose 5 pounds and I drop down to 195, I would compare that change of 5 pounds to the original 200, not the after picture. It's always compared to the before picture. What was it before the change that you're measuring? And then a different but very related idea is percent error. Percent error, the essential question here is how is it similar to finding percent change? Well, you'll see from our little formulas here that it's very, very similar. Percent error comes into play. A lot of times people think error and they think a mistake, but really anytime I am measuring something, it's never an exact thing. So if I am measuring with a ruler, I'm going to be a little bit off of what the actual measurement is. How much I am off, if I'm off by an inch and it's a marathon race, that's no big deal. But if I'm off by an inch on laser eye surgery, all of a sudden we have huge issues. So a percent error is how off you are compared to what it actually should be. So there we go. How off, and I'll put that in quotes, how off you are compared to, and I'll put a little arrow down here, compared to the actual or what it should be. So if I am doing a measurement or I'm estimating, like if I estimate that I have 25 students in my first hour class, how many students I actually have compared to how far off I am, that comparison is what percent error measured. How far off you are compared to what it actually should have been. So what you're going to be doing on these is you're going to be finding a change on percent change, and you're going to be finding a difference for percent error, but it's really the same idea. You're going to be doing a subtraction problem. And I would always do the subtraction, the big number minus the small number, and just be okay with if it went up, it's an increase. If it goes down, it's a decrease. However, for percent error, you don't care whether it's up or down. All you care is how far off it is. So on this one, this difference, you won't ever put a negative number in here. It's just how far off are you from what it should have been, and then we'll do that percent calculation. Most of the time I'm going to be using this percent times original equals change and percent times actual equals difference. Do we notice this is really the same format we had before? Percent times whole equals part. This part here is how much it changed compared to the whole original one. For percent error, it's how far off are you? What is the difference compared to the whole actual what it should be? So we're going to go through a series of problems here. Each one of these I'm going to do my little calculations, but if you did well on 3-2 and 3-3 homework, then this shouldn't be too bad. It's just an application of those particular proportions or equations. So we are going to go into the first little situation here, and this is kind of illustrating the purpose of percent change. So here we have a situation where Nadia lives in a town of Preston. So here's Preston's information. Quinn lives in a town of Elm Ridge, which has smaller population. Nadia and Quinn each claim that her respective town's population is growing more rapidly. Well, what we can do is we can see, okay, Preston's population last year and population this year, the population did go up. It certainly did go up. And we look at Elm Ridge's, their population went up as well. Now, how much did they go up? Well, that's what we can do here. We can do a little calculation. So I am going to do a calculation here for Nadia's. Nadia lives in the town of Preston. So for Preston, I'm going to figure out how much did this change. So that's just a subtraction problem. I'm just going to take 5,702 and subtract the previous year's population. And I'm not really super interested in seeing that arithmetic. I just want to know what it is you're doing there. So 5,702 minus 5,589. And it looks like it's 113. So what does that mean? Well, it means the population changed by 113. It increased by 113. So there's my increase. If we do the exact same thing for Elm Ridge, this year it's 1926, and last year it was 1870. And if we do that subtraction, 1926 minus 1870, and it's 56. So if we look at it just based on raw numbers, Nadia is correct. She says, why might she argue that Preston's population is growing more rapidly? Well, it increased by 113 people, whereas Quinn, his Elm Ridge population only increased by 56. So based on raw numbers, Nadia is correct. Preston is growing more rapidly. It's growing at 113 compared to 56. However, if we take a look at it, this increase is roughly, very close, roughly twice this. But look at the population. So the population of Preston is significant. It's like 3 times the population of Elm Ridge, but it only increased by twice the number of people. It makes sense to me that if the population is higher, we would expect the increases to be higher because there's more people to repopulate. So if I were Quinn and I wanted to convince somebody that Elm Ridge was growing more rapidly, I can't use just the raw numbers. I have to use this number compared to what the actual population was. If I do that, that's getting into percent increase. Both of them are increasing, but if I do a percent increase, we can more easily compare the changes. So raw numbers, Preston's growing faster, but percent increase, since 56 is about half of 113, but this population is only about 1/3 of it, I think Quinn could, if she used percent increase, could quite easily convince me that Elm Ridge is growing more quickly. And if you think about it, if there were one person and they increased by 50, that would be a smaller increase than either of these, but that would be a huge change from 1 person to 51 people. So just based on the raw number, it's not a great measure. I think the more logical way is to use a percent increase. And we're going to go through several examples, so I'm not going to spend time and go through the calculations here. But based on raw numbers, Preston grows faster. Based on a percent increase, since this population is smaller, significantly smaller, its increase is a bigger change than the increase was for Preston. Percent increase makes more sense to you because to use it because it compares to what the population was, that we have actual comparison of the numbers. So let's do an actual example here where we can do some calculations, and we'll do them right here on the page here. So here we go. Pretty simplistic little problem here about an alligator here. I think that's an alligator. Yeah, an alligator. Percent change describes how much a quantity has changed relative to its original amount. That's a key thing, to what it was originally. The percent change can be an increase or a decrease. So if this was last year's alligator and this is that same alligator this year, I can see quite easily from the picture and the diagram that it grew. So this is going to be a percent increase here. I can tell just by looking at that. And it wants to know, what is the percent change? Well, to do the percent change, all we're going to do is say, okay, how much did it change? And then I'm going to compare that change to the original amount, never the after, always to the original. So this is what it was originally. This is after the change. The change I can calculate just by doing a simple little subtraction. This is so easy we can do it in our head. But then I compare that change to what it was originally. So to get the change, I just take 38 minus 32. So 38 minus 32 equals 6. So this alligator grew 6 inches. Not a big deal. Now if it was a humongous alligator growing 6 inches, or a little bitty one growing 6 inches, those changes are not the same significance. So that's what percent change is all about. So to get percent change, we can go about it different ways. I'm going to use a percent equation. So here's what I'm going to do. I'm going to use percent change times the original equals the change. One option, you can use a proportion if you'd like. So I don't know the percent. That's what I'm asked for. So I'm going to call that P. The original is that 32. And the change we just calculated was 6. And so now I'm going to divide by the 32 because that's the number with the variable there. So I get P equals, and I get 6 divided by 32, and I get 0.1875. But remember, that is the decimal form of the percent. So if I bump this over 2 places, the percent increase is 18.75%, and I'm just going to add the word increase there. I didn't do any calculations to figure out that it was an increase. I just knew that it went up. That's all it is. Don't make a big deal out of that, certainly. So that alligator's growth rate is 18.75% increase when it went from 32 to 38. Pretty straightforward. If you want, you can use a proportion. I will use a proportion on this next one just to show you that it doesn't really matter which way you do it. This next one asks for a different sort of question though. What will the length of the alligator next year if its length changes by the same percent? So it's 38 now. And so what this question is asking, if it grows at this rate another time, so if it goes from 38 to a higher amount, if we have an increase from 38 to something else, what will it end up being if it grows at that same rate? Well, let's think about it. In this equation, the original amount is now the 38 because we're starting at this year. And this year is what will change for next year. So the original amount for this question is going to be the 38. And we know the percent. So I know both of these pieces. But let's do it with a proportion here. The proportion, Pretty straightforward. It is the change compared to the original is the percent change out of 100. And so of these pieces, what do we know? Well, we know the percent. We know it's 18.75. We know it's originally 38 and it's going to change to something. And so we can calculate the change. So let's do that. Let's throw the numbers in here. I don't know the change. I'm going to call it C. I do know the original is a 38 equals, and it's 18.75 compared to 100. And then we cross multiply and divide on these. I'm going to step through that process pretty quickly. 18.75 times 38, and then we'll divide by the 100 because that's our coefficient, the number in front of our variable here. So then I'm just going to 18.75 times 38 divided by 100, and I got 7.125. C equals 7.125. Now if you're thinking, wow, that got shorter, remember this is the change. This is an increase of 7.25 inches on the 38. So to get the actual length, I'm going to have to add 7.125 inches onto the 38. So if I go 38 plus 7.125, I get 45.125. And so next year, if the alligator, that is not the increase anymore, that's the next year's length. So next year. So again, I don't care if you use the equation, the proportion. I really don't. It just, whichever you're more comfortable using. That's why we went over both of them, to give you that option. Now you may notice that the increase was 18.75%, and then we did that same increase again, but now it changed by more than it did before. Before it changed 6 inches, and this time it changed 7.125. And this question down here at the bottom kind of gets at that. Why is the increase different from year to year, even though the percent change stayed the same? And it's simply because of what it's being compared to. This first time it was compared to 32. This second time it's compared to 38. If we do another year, it would be compared to 45.125. So if the percent stays the same, it's being figured of an ever-changing original number. So it's always being compared to the previous number. What changes? So you shouldn't expect the amounts to stay the same, because what you're comparing that percent to is changing over time. It went from 32 to 38, and then if we did it another year, it'd be for the 45.125. So again, percent equation, percent proportion, whichever you prefer. I'll probably do the percent equation most of the way through the rest of it here, because that's the method I prefer. So I'm going to move on to next little situation here. I'll do a little bit of scrolling here. I added this little question here to illustrate a point that some people get confused. If 100 changes to 80 or 80 changes to 100, well, we can see one of them went down, one of them went up, but is the percent change the same or different? And some people say, well, it changed one to the other, so yeah, it'll be the same, but it actually isn't. If 100 is changing to 80, it changed by 20, right? It went down 20. If 80 changes to 100, it went up 20. So you might think, oh, well, change of 20 each way, but think about how percent change works. This 20 change would be compared to the 100 original, whereas this 20 change would be compared to the 80 original. So if you think about it, 20 out of 100 is a 20% change. 20 out of 80 is actually a 25% change. 20 out of 80 reduces to 2/8 or 1/4, and that is 25%. So it's what it's being compared to that makes the different answers. This change of 20 is compared to the original 100. This change of 20 is compared to the original 80. So you don't get the same result. This would be a 20% decrease, whereas this would be a 25% increase. It's a larger percent because you're starting at a smaller number. So that 20 is a bigger part of 80 than this 20 was of the 100. So just be careful that you always have to compare it to the before number. So let's do one where there's a decrease. We just saw a decrease there. It's no big deal. It's just anytime something goes down, you're going to have a decrease, and then the percent change is going to be compared to what it was before the decrease. So in example 2 here, last year website had 40,000 visitors, and this year it had 37,000. What is the percent change in the number of visitors to the website from last year to this year? So what I'm going to do is I'm just going to find the change, and I do that change by just subtracting. I'm going to take 40,000 minus 37,000, and I don't need a calculator to do that because I can do basic arithmetic there. So that change is 3,000. So I need to compare this change to what it was before that change. And before that change, it was 40,000. So in my percent equation, I have percent times the original before the change is going to be 40,000 equals the actual amount of change is the 3,000. So then we have a variable. It would be better to use there, so I'm going to get rid of that percent symbol there, and I'm going to replace it with the variable p. We already know the visitors went down, so this is going to be a percent decrease. Don't ever make that a complicated part of it. 40,000. I'm dividing by the coefficient of my variable p there, and so I get p equals 3,000 divided by 40,000, and I get 0.075. But remember, that's the decimal form of the percent. So this is a 7.5%, and since it went down, it's a decrease. If it had gone up, I would have said it's an increase. Don't make that a complicated deal there at all. So again, you can use a proportion if you like, but find the change, compare that change to the original. That's all we're doing here on percent increase and decrease. So let's do another quick little sample here. Due to excessive Christmas shopping, my bank account dropped from $800 to $200. What was the percent change? Was it this an increase or a decrease? This should be a brutally obvious question because I said it dropped. It's going down. It's a decrease. So step through it. First thing, find out what was the change. The change, well, it went from 800 to 200. So it changed by 600. And then I compare that 600 to what it was before it dropped. So I have to say the percent, supposed to be a time sign, percent times what was it before the drop? Well, it was 800. And how much did it change? 600. So I take this change that I calculate and I put it right here, and this is always what it was originally. And then I'm just going to divide by 800. And I'll cancel there, and I get P equals 0.75. I didn't need to type that one in. I kind of recognized it. But remember, that's the decimal form. So that is a 75% decrease. Now, when I made up that problem, I thought, could you have a percent decrease over 100%? And if you think about it as a bank account, I suppose you could, because there could be $800 and then I could spend more than $800 and go into the negatives. So if it's possible to go into the negatives, then you can have a percent decrease of over 100%. Now, a percent increase of 100 just means it doubles. If it was 100, it went up to 200. It increased by 100%. So a 100% increase is a doubling. So if it increases something dramatically, you can have a serious percent increase just using these same numbers. If it had gone from 200 to 800, it still would have changed 600. But I would be, if it started at 200, I would have a 200 here. We would end up with a 300% increase if I did from 200 to 800. So it definitely makes a difference which number you're starting at. So always be careful that you put the original or starting number right here next to the time sign, and then the change always goes over here. So let's move on to a slightly different but very related topic: percent error. So anytime you make a measurement, anytime you do an estimate, anytime you make a part, it should be a certain size, but it ends up being your estimate's off, your measurement's off, the part is not what it actually should be. How far off it is, that's called percent error. So percent error is going to be calculated the same sort of way, only we need to always compare to what it should have been. So if we look at this example here, Sean estimated that the attendance at a college lacrosse game was 3,000. The actual attendance was 3,296. So he was a little bit off. So what is the percent error of Sean's estimate? Well, I want to see, okay, how far off is he? And that's what's shown right here. He's off by 296. I don't care whether he was above or below by 296. So that's what the absolute value bars are. For percent error, you won't ever have negatives. Just subtract so you get a positive. So he was off by 296. But how big of an error is that? If you were off by 296 out of millions, that's really good. If you're off 296 out of 300, that was absolutely terrible. So to get a feel for how big of an error his estimate had, I need to compare this offness, this difference. I need to compare it to what the actual attendance was, not his guess. I don't want to compare how off his guess was to his guess. I want to compare it to I want to compare it to the truest number that we have, which is the actual attendance. So I typically will flip-flop this. I'll put the percent error times actual attendance on the left side. So that's what I'm going to do. The percent error times the actual attendance, which was 3296, equals the difference in the attendance and what he estimated, which was this 296. So you see, it's really the same thing we did for percent change. Find a difference, put that difference here, and put the original, or in this case, it's the actual attendance. And now it may not be a super pleasant answer. I'm not thinking this is going to be real nice, but I'm going to solve it here. 3296 is what I'm going to divide by. So I take 296 divided by 3296. And yeah, I get a crazy decimal that goes for a while, so I get 0.0898 on and on. So I would say that is roughly a 9% error. And don't think of errors as being, oh, you messed up. Errors happen all the time. Anytime you measure something, it's never going to be exact, because you're measuring it and you're using a measuring device that may or may not have very good precision. It's not going to be exact. When you estimate, it's okay to be off. It's an estimate. So I'm not surprised at all that Sean's estimate was off. In fact, 9% off is not too terrible at all. Depending on how serious the situation is, determines how much off you're allowed to be. So if it is like the distances for laser eye surgery, you better be really close to what it's supposed to be. But here, does it really matter that he was 9% off? No, doesn't really matter. So let's do another one. This one is about making a bolt to a certain specification. So the specification of the length of the bolt is that it's supposed to be 4.75 inches. This is what it's supposed to be, or what it should be. However, the machinist makes a bolt that is a pinch longer. If we look at it, this is 4.75 and this is 4.769, so it's a smidge longer. And you may know, well, is that okay for it to be a little bit longer? Well, different applications have different specifications for things. We got to know how big of an error is that so we can determine whether it is an appropriate bolt or not. Again, when you're making stuff, you're not going to be able to make it exactly 4.75. You just have to get it really close. Now, how close? That's what percent error is. So to find the percent error, we need to find the difference. All I do is I subtract to get a positive number. I don't bother ever with getting a negative. I take the big one minus the small one every time. So 4.769 minus 4.75. And when I do that subtraction, I get 9, 1. I get a difference seemingly pretty darn small, 0.019. And then to figure out what percent that is, I need to compare to what should the bolt have actually been. What should it have been is the 4.75. So I need to compare this difference to the 4.75. So I'm going to take percent times what it should be equals the difference. And so the percent times what it should have been is the 4.75 equals, and the difference between what it should have been and what it ended up being made at is that difference of 0.019. And so when I go to solve this one, I'm going to divide by the 4.75 because again that's the coefficient of my variable there. And so when I type this in, not expecting a nice answer, 0.019 divided by 4.75. Wow, it's crazy nice. I get 0.004, which, if you move it 2 places over, that is 0.4% error, which is very low error. In some applications, it might need to be a smaller error than that, but that is really close. And if you think about it, that is roughly 0.02 of an inch off. That's hardly noticeable. So it was, if you just look at it, if this was 0.02, it is really close to that. That would be 0.02 of an inch. So it is a tiny, tiny bit long. So it would probably be fine unless, of course, it was some sort of serious application where you couldn't have it be longer than that. But that is a really low percent error. So if you look at it, pretty straightforward. You take the difference to see how far off it is, and then you always compare to what it should have been. So Sean's estimate should have been the 3296 that it actually was. This bolt should have been the 4.75, so that's what you compare it to. You don't ever want to compare it to a mistaken product or a mistaken estimate, because then that'll dramatically throw off the percents. Like if he estimated the attendance as 1 billion, I certainly wouldn't want to compare how far off he was to his billion. I would want to compare it to what the actual was. That should kind of make sense to you there. So let's take a look at one more little deal here. Oh, it's kind of chopped off. It's the same sort of deal. This is the ending little summary of it. To do a percent change, be it an increase or a decrease, you find the change, and then it's a percent of the original. If we are doing percent error, this percent is a percent error, and this original amount is what it should be, what it actually should be. And then the change for percent error, I don't care whether it's above or below, I just want to know how far off it is. So hopefully these examples will help you do the homework here. I assigned, what is that, 6 problems there. For each one, I should see either a percent equation or a percent proportion. And you decide, as long as you are showing your work appropriately, I will have no problems with it. So that is lesson 3-4.